afternoon session, which the idea is to give the word to all the scientific areas that we have here in the faculty, as I said, from the fundamental to the applied science. And we will start with mathematical sciences. And I invite Professor Florentino from CMAFcIO to give his talk about geometry, algebra, and thank you very much.
Okay, so hello, good afternoon. I would like to thank the organization of this event for the invitation. For me, it's a pleasure to talk to this diverse audience and scientific audience, nevertheless. And but it's also a challenge, right? It's a challenge because I want to present some mathematical ideas, but I need to keep all the technical details to a bare minimum. And but still I want to convey some interesting concepts of mathematics and ideas, and give a glimpse of what would be, an idea of what can be mathematics, or some themes in mathematics that some topics in mathematics that are in the intersection of geometry, topology, and algebra. And so there would be many possible choices for this general talk. And I decided to talk about mainly two concepts: curvature and the Euler characteristic, which I think they are good candidates to give you some intuition and explain things without detail. Then I'll talk a little bit about commuting matrices and present some, in the end, some outlook and some conclusions, maybe some open problem. Okay, so what is curvature? So start with a plane curve, a curve in the plane. Take a point. At every point of the curve, there will be a circle, a unique circle, which best approximates the curve in that point. That's the oscillating circle. What is a curvature? The curvature is just the inverse of the radius of the oscillating circle. And this coincides with our intuition that if the oscillating circle is very small, then the curvature is very big, and vice versa. And then the portion of a straight line, let's say the curvature is 0. Okay, what about surfaces? Okay, so this was the idea of Gauss. Gauss thought of the curvature in the surface, and his idea was take a surface in 3 space, look at all possible slices of that surface that are perpendicular to the surface at a point, and look at the biggest circle of that curve, and look at the smallest circle of the curve, take their curvatures, multiply. And that's the scalar curvature, also called the Gaussian curvature. And I put there plus and minus sign, because if the circles, one is one direction, and the other circle is on the other direction, then the curve will be negative. Okay? So what was his theorem with this definition? Was the following. The scalar or Gaussian curvature only depends on the metric. This means it only depends on the distances measured within the surface. So basically, it does not depend at all in the way that the surface is embedded in space. For example, I forgot one very simple example. This piece of paper has 0 curvature because, of course, if I put it flat like this, then we have 0 curvature. But if I bend it, it still has 0 curvature because one direction at least is 0, and 0 times everything is 0. So I can bend slightly a surface, and the scalar curvature is invariant. He thought that this theorem was so nice that he called it theorema egregium, like the nicest theorem he could show about surfaces. Okay. However, the curvature is not invariant and the stretching. Why? Because if I have a balloon or let's say a sphere, and it has a radius, I increase the radius, then I decrease the curvature, so the curvature is not invariant. However, there's a very interesting notion that's going to be invariant. It's the total curvature of, let's say, a closed surface. It's just the integral of the curvature along the whole surface. And that's going to be invariant. This is something that I think Gauss didn't really think too much about it, but neither Bonnet, apparently, but it's now a very famous theorem called Gauss-Bonnet, and it says that the total curvature is invariant under all deformations except cutting or gluing. So this is an example of deformation, and the total curvature of those surfaces is the same, regardless of the area. Okay, so one then computes, of course, this computation is not trivial, that anything that's deformable to a sphere, the total curvature will be 4 pi, because if I take a sphere of radius 1, then 4 pi r squared is the area of the surface, so the curvature is 1, so there's the 4 pi. Then if I take a torus, the curvature is going to be 0, because inside the torus, there will be negative curvature that compensates the positive curvature outside. If I take a two-fold torus, etc., the curvature starts being negative. And if I take a torus with G-fold, the curvature would be this formula, where chi-s appears. What is chi-s? The Euler characteristic of a surface. And why do I write it like this? It's because there's another interpretation of this Euler characteristic, by Euler, of course, that comes from studying convex polyhedra. If I study, of course, any convex polyhedra, then I take the number of vertices, the number of edges, the number of faces. This alternating sum always equals to 2. But putting together the two kind of observations, we get that we can do anything for any surface, not necessarily convex. So if I take this surface, well, it's like a weird surface, but it's like not really triangulated. Let's call it quadrangulated, but that's fine. I mean, we can just compute the number of vertices, edges, and faces, and it will give 0. Why? Because it's a deformation of the torus, and so we get this another form of the Gauss-Bonnet theorem. Okay. So now, what about polynomials? What do polynomials have to do with this? Well, okay. Let me just say that some polynomials, like this one, x squared plus y squared equals z squared, have many, many solutions. Those are called Pythagorean triples. There are infinitely many such triples. We also have a very famous result saying that this equation, as long as the exponent is bigger than or equal to 3, there are no solutions to this polynomial equation. No solutions in integers. Okay, this is the main point. And this was Curvature's theorem in quotes, and this, of course, called now the Weil-Taylor theorem from 94. More interestingly, at least from my point of view, is the following question: how many integer points are there in it that solve the polynomial equation, like this one, x squared plus y squared equals n? And famously, Jacobi presented the complete formula for the number of solutions. D1 n is the number of divisors of n which are congruent to 1 modulo 4, and D3 are the number of divisors of n congruent to 3 modulo 4. And if you take this circle here, which I wrote as being having radius 5, then n is 25. The divisors of 25 are 1, 5, and 25. Both are all 3 are congruent to 1 modulo 4. So we have 12 points here. This is a very interesting theorem by Jacobi. Another very interesting theorem on this kind of question, much later, Falkings, he won the field medal for this theorem, is that the first glimpse of a strange relation between the Euler characteristic and the number of solutions of polynomial equations. This is something I cannot explain in no detail, but let's take a polynomial with integer coefficient that describes the smooth surface with Euler characteristic negative Euler characteristic, which means that the genus is at least 2. Then it has only a finite number of, let's say, integer solutions. What I'm not explaining is how can you get this polynomial to describe a surface? Because I'm not talking if x and y and z are real numbers, complex numbers, or whatever. But anyway, you can see that this equation, initially, you can think of it as a circle, right? So take 3 variables, you can think of it as a surface in some way. And it's just that I want to solve the question for integers. But if I take real numbers, not complex numbers, it will describe what is called a manifold. Anyway, but the theorem is still amazing. The fact that the Euler curvature is the Euler characteristic negative gives a finite number of integer solutions. So more generally, one can define the Euler characteristic for any space of any dimension, and in particular for this this space is called algebraic varieties, which is just at least for this solve the set of solutions of a system of polynomial equations in many variables, finite number of them. Okay. And I want also to give this definition, which is of a Lie group. A Lie group is a very important concept because it quantifies the notion of symmetry. Symmetry in physics, symmetry in in fact, this has been applied also to chemistry. So Lie group, for me, this is a simplified definition, is a closed subgroup of the group of invertible matrices which have determinants different from zero. Two examples. One is the space of all invertible matrices, let's say with complex coefficients. The other one is the space of orthogonal transformations in Rn. Thus satisfies A transpose times A is the identity and the determinant is 1. And I like to call this the nicest theorem that doesn't have a name because it's a relation between, it's a computation of an Euler characteristic of a Lie group. When it's compact and has positive dimension, then the Euler characteristic is 0. Well, some interesting results. And of course, I would need to define the Euler characteristic for a higher dimensional space, but it's in the same way. I triangulate a space with higher dimensional cells, and it's an alternating sum of the numbers of elements in each dimension. Okay, so now commuting group matrices. I'm going to at least say one theorem that I recently was able to show. So, and it's about commuting matrices. So two square matrices commute if their product is equal either way. And I consider this set, which is an n-tuple of elements in G that pairwise commute. Don't worry about that zero there, but I will. It's just a path component of that space. So you can ask, but this is an algebraic variety actually. I was forgetting to say, but why? Because it's defined as the equation of the entry of the matrices in G. Okay, so this is an algebraic variety, and we can compute its other characteristics or try to compute its other characteristics. Why do we care about commuting group matrices? Well, I could say many things, but maybe this is a motivation from quantum physics, because going from classical physics to quantum physics replaces functions by operators, so matrices basically, and the evaluation of functions by brackets, let's say. Of course, I'm being very vague here. But the interesting thing is that operators that commute behave classically. So matrices that commute somehow correspond to quantum observables that can be simultaneously measured. So this may be one motivation to the commuting matrix. Okay, so how many commuting group matrices are there over a field of prime characteristic? Okay, maybe now this is another jump, but I can just think of this finite set, numbers from 0 to p-1 as a field, because I can multiply them mod p and add them mod p. This will be a field. And recall that this space is given by polynomial equation. And we found this formula for the number of points in this space up to conjugation. This quotient by G is the conjugation. And this is in a very exclusive formula. It only involves the Val group, which I cannot explain, but it's like also a symmetry associated to the Lie group, and the determinant so this is the characteristic polynomial of the action of every element in the Val group. And the other characteristic has a very similar expression. For example, I can just evaluate this determinant and, for example, consider 3 commuting matrices in S of 5. It will be this number of finite number of points in a finite group. Okay. So conclusion. The Euler characteristic is one of the simple properties of a space. This is at least a concept I want to convey today. But it's also extremely useful. It's related to total curvature counting, surprisingly, and many other global properties. There are also many other refined invariants that I cannot talk today, but they are studied in a master course on algebraic topology, let's say. But this is the most important thing, is that the qualitatively different spaces cannot have the same invariance. So for example, two vector spaces, if they have different dimensions, they cannot be the same. Two surfaces, if they have the different genus or different Euler characteristics, they cannot be the same. And this can be applied also to varieties of groups, etc. That's what I worked. Okay, mystery question. Can one detect curvature by counting solutions of polynomial equations? This is a very strange topic for me, and it's a mystery because curvature is intrinsically continuous concept, whether counting solutions with integers, in integers is fundamentally discrete nature. So in fact, I don't know the answer to this question. I have no idea, but that's why mathematics research is very important and very interesting. Thank you.
So we now move